Okay, good morning, everybody, and welcome to today's course micro event on supply chain decision making and system dynamics modeling. Today, we have two speakers with us, Dr. Yossiri Adulyasak from HEC Montreal and Dr. Yvonne Taylor from Policy Dynamics Inc. It is our great pleasure to have them with us today and to listen about their experience and background in these areas. I will begin with a brief bio first and then pass it on to the speakers. Our first speaker is Dr. Yossiri Adulyasak, and his talk is entitled Analytics and Stochastic Optimization for Supply Chain Decision Making in Uncertain Environments. Dr. Yossiri Adulyasak is the Canada Research Chair in Supply Chain Analytics and an associate professor at HEC Montreal and an adjunct professor at the Université de Montréal, Diderot. Prior to joining HEC, he was a postdoc at MIT and then a data scientist at JDA Labs, which is now known as Blue Yonder. To date, he has co-authored more than 40 research articles in the areas related to supply chain management, analytics, artificial intelligence, and optimization, which appeared in prominent research journals, including Operations Research, Inform's Journal on Computing, Transportation Science, Manufacturing and Service Operations Management, Production and Operations Management, Transportation Research B, Journal of Artificial Intelligence Research, as well as top-tier machine learning and AI conferences such as NEUR IPS and AAAI. Drawing upon his scientific expertise, Yossiri advises leading Canadian and international companies as well as startups on the implementation of advanced analytics in various supply chain applications. He is also a co-inventor of 5 patent applications in retail and supply chain analytics and has been awarded several prizes from academic and industrial organizations during his tenure. It is our pleasure to have Dr. Yossiri with us today. I pass it on to you.
Hi, hello. So thank you, Anjali, for the introduction. My talk today is going to be the theme around the analytics and stochastic optimization, basically in the context of supply chain. So basically, as you see on the screen, there are different area of analytics from descriptive, predictive, prescriptives. And in our group, we work on multiple applications from demand, retail, distribution, fulfillment, inventory, and also the production planning. So from the very beginning until the end of the supply chain. So what I want to give as an example, this is also an example I like to give in order to basically motivate the application of why decision-making uncertainty could actually be challenging and difficult. So let look into this simple example. In this illustration, let's say you want to go from point A to point B. You basically have two routes that you can choose, the route number 1 and also the route number 2. So let's pull out some statistic about these two possible options. In number 1, let's say the average travel time is about 12.4 minutes. Probability is basically about 20% that you're going to take less than 20 minutes, right? So you want to go from A to B, and then you have 20 minutes in order to reach the deadline, right? And the average time 12.4 minutes, you have 80% chance that you're going to be there before the deadline. In the route number 2, the average is basically 12.2 minutes. Actually, it's shorter than number 1. And then probability of reaching the deadline is actually 95%. So if you see from these statistics, right, it's pretty clear that, from the average perspective, route number 2 is actually better. From the probability perspective, route number 2 is also actually better. So it's pretty clear that number 2 would actually give you a, better chance than so the average in terms of the travel time. So based on this statistic, I think many decision makers probably actually use this information and choose to take the route number 2. So let me show you, let's say, if in turn, instead of having, these average and also these probabilities, route number 1, basically it turned out that there's 10 minutes with probability 80%. And if there's a delay, maybe there could be some traffic or maybe, there's some congestion in some certain, intersection. It could take, instead of 10 minutes, it could take about 22 minutes, but with probability 20%. All right. And number two, on the other hand, it could be pretty quick with high probabilities, but it could be a highway, with when there's some accident because there is a lot of traffic, that could actually cause, a lot of basically congestions and also the time increase in terms of the delay. So if there is, any case where it encounters some situation where, the traffic is blocked, it could actually increase to 54 minutes. Maybe you need to take the long detour. So based on this, you have to be there 11:20 in the morning. Um, Basically, some of the decision maker looking into this information might actually, decide that maybe route number one is actually, also a good idea. Like 10-minute probability, 80%. If you are late, it's gonna be 22 minutes. But in this case, if 11:20 is actually, very, very hard deadline, maybe some decision maker gonna choose a route number two. But 2 minutes probably is not too bad. Actually, these, two information come from the same distribution or from the same, support of the uncertainties. Basically, initially, those who look into these, statistic and actually choose a route number one, there could be people who look into this statistic or this information, and sorry, this one you would choose the route number two, and this one you would probably choose the route number one, right? But these actually come from the same, basically, statistics or the support. So you can see that in terms of decision making under uncertainty, there's no single simple dimension that you can consider. For example, if you want to optimize a cost, if you assume that everything is known with certainty and you can write a perfect objective function, maybe you can minimize cost. But when you deal with uncertainty, this is also the aspect in addition to just the value, right? This is a probability, this is the risk, this is also the expected value that you need to look at. So there are additional dimensions, right? What is the main objective? Are you going to try to minimize the expected time, in which in that case it should be route number two, or you want to actually minimize the tardiness in case, including the case when there could be the delay. Maybe in that case, route number one could actually be better, right? So it also depends on the risk preferences, also the constraint, in a lot of supply chain applications and also inventory planning. We also look into something like, buffer time, safety stock. Those are the tools that we actually use to deal with uncertainties. The third aspect is also the component of data availability, right? How can you get such statistics or useful information so that you can make informed decisions? Data availability is also an important thing that you need to consider because, based on the data, you estimate the parameter you need for your models. And then if the data is very limited, how can you deal with that? The last one that the talk would cover a little bit today, even if you have, this model set up, you have data availabilities, these are sort of the aspect of how you want to represent these uncertainties. Do you have, for example, you want to represent it using empirical distribution, you want to use scenario set, or you want to use any other form, right? In robust optimization, you may have different form of uncertainty set or even ambiguity set. Um, what also make it quite difficult is when you actually have multi-stage decision making. So what it means is that you can anticipate what's going to happen, and given that conditional on what's going to happen, then you're going to make subsequent decisions. So this is a component of adaptability in the sense that your decision may be adapted based on what you anticipate that it's going to happen in the future. So if you think about in that case, it could be represented as very large, scenario trees. You anticipate that this demand going to happen. Given that this demand going to occur, then you're going to make these type of decisions. Um, the other case that become also quite interesting, but also at the same time would be quite difficult to do with in the case when uncertainty could also be endogenous. For example, in the retail, you need to actually, observe the demand, use the demand for the inventory planning. But you know that, pricing decision basically can affect the demand, right? You reduce the price, you may change the demand. There's some, stock out, maybe the demand of other product would increase because of the substitution or the behavior of the people. So decision that you make can actually impact the uncertainty and actually impact the actual observations you're gonna observe in the future. So this type of uncertainty could also be very challenging to deal with, and there are many techniques that people try to use to deal with that. And also the other one that is an aspect that in our group we try to tackle quite a bit is basically if you try to tackle, this type problem, in many cases, you may need to deal with a lot of scalability issues. The model becoming more complex. If you consider like stochastic optimization using, random samples, you need to draw a number of samples, and essentially you grow the size of the model, sometimes exponentially. How can you deal with that? What is the technique you can exploit in order to deal with that situation? All right. So the focus of this talk, um, is basically to demonstrate some value of the stochastic and also robust decisions, and also the value of decision adaptability. So in multi-stage decision making, when you face with uncertainty, but you don't know the full uncertainty at the same time, for example, you need to plan for your inventory. You may not know the demand from now until the end of the year, but 1 week from now, you're going to be able to observe the demand. 2 weeks from now, you're going to get additional information on the demand. How can you use such an information to help you make better decisions? Right? And the focus of the talk is going to be around the supply chain application, because this is the main domain of research in terms of applications that we focus on in our group. So this is another illustration, right? Why doing sometime, deterministic optimization, based on using the expected value of the input may not be the best idea, right? So, this is the very popular illustration published on the, I think, Harvard Business Review long time ago, to demonstrate the flow of averages, right? So this guy want to cross the river. He know that it's 3 feet deep on average, right? And then you can see that the average may not be the best value. So planning for the average, in many cases, may not be the ideal, approach that you want to use when you actually deal with the uncertainty. All right. So, by the way, if you have anybody has any question, feel free to raise your hand or interrupt me if you want to do so. Um, One of the things I want to give as a perspective of different tools we actually usually use in order to deal with uncertainties. On one hand, we have, the stochastic programming. Mostly we assume that it's a known probability distribution. And then we usually try to minimize the expectation, right? So it could be expectation of the cost, could be expectation of the revenue, or it could be also a different form of the objective function. It could also be maximizing service level subject to certain expected total cost, or it could be different form of objectives. Um, on the other hand, there is a technique around what we call robust optimization. So instead of describing uncertainty using probability distribution, and basically take random samples, we can actually describe distribution using some statistic or some information. For example, it could be minimum, maximum, could be polyhedral uncertainty set, could be the well-known budgeted uncertainty set that has been introduced, I think, since 2004 and still being used until now. And in most cases of robust optimization, people would try to minimize the worst case performance. On one hand, you don't have the full information about distribution, so it essentially could be difficult to obtain or calculate the expected value, right? So in that case, where the goal and the main objective of this type of technique is also to minimize again the worst case, but as you can see, in some cases, it could be overly conservative. So these also, a lot of papers and also recent techniques that try to reduce the conservativeness of the robust optimization. So there's also the combination of the two, the people call it in different way, and there are many different forms. So I kind of simplify a little bit in the sense that you can also combine the two type of techniques, and some people call it robust stochastic optimization. This also the version of robust optimization, such as distributionally robust optimization, that can also reduce conservativeness of the decision-making process. So in this case, we attempt to combine the two. So one possibility is maybe you can associate the notion of scenarios with ambiguity set. So you have probability associated with different ambiguity set or uncertainty set. And then you try to minimize against the worst case, but the worst case of the distribution. Right? So in terms of the other complexity that we discussed about, the decision stages can also be single stage, two stage, or even multi stages. And that actually make it difficult, right? Because in two stages, you have one point where all realization become available. And then there's another recourse decision you can basically use to react to such realizations. In multi-stage, which is the most difficult case, you're gonna have uncertainty that get revealed over time. But then after, part of uncertainty is known, then you can make some decision. Then another uncertainty is basically revealed, and then you can basically make another decisions, right? So one of the things that we tackle in our group is basically we cover different area of supply chain. So we have some research paper that focus mainly on the forecast or analytics. Mainly we try to quantify and we try to tackle the challenge around the forecast and also around the estimation of important input and parameter. For example, this demand predictive analytics using machine learning that we use in some of our work. This is the first part that become a very important input, the forecast, which is the main input on for many processes that come after in supply chain. There could be also many application on the supply and production. For example, the sourcing, where to source a product, and how many unit you need in different period of your planning process. Production planning, procurement, also material planning, which is also one of the topic I'm gonna cover today. And it could also cover also capacity management and many problem around the production and scheduling. The other area is also around the inventory and fulfillment. Basically, how would you manage your inventory? How much inventory you should keep? What is inventory policy? What is the safety stock level that would be good for your business? Also, I also work quite a bit on the transportation, meaning the routing and scheduling. Or the assignments, different form of routing under uncertainty, especially the travel time or even service times. So this talk will cover the topics that are actually included in these three papers below. So the first one is the robust delivery with better information. We look at it in the context of drone delivery. This paper is already published and available on manufacturing and service operations management. The other two papers that touch on the same or very similar topic on the material requirement planning are actually already published. The second and third paper. So let me cover the first aspect of the supply chain. So this first area of application touch on the decisions in the supply part and also the inventory management, which is a production and material requirement planning. So this in this type of area, traditional, especially for the inventory management, most technique focus on single item, single location. We also have the other area of research where it look into multi-echelon, multi-item network, but mostly the model that is used is a deterministic model, meaning we assume that the forecast is known with certainty, but then if the forecast is not perfect, or there is some uncertainty, then we can use the technique from the inventory management to calculate safety stock and use the safety stock in the planning process. On the other hand, what we try to propose here is basically we want to actually come up with the systematic approach to consider uncertainty and then make the recommendations on how much you should produce or how much you should replenish at different times um, in your supply chain network. So basically, we want to upgrade the traditional material requirement planning and distribution resources planning in order to make sure that the decision can basically incorporate the consideration of different form of the uncertainties. So essentially, you can see it as a joint optimization of the cycle stock and safety stock in the supply chain network in the context of MRP and DRP. And since MRP and DRP is a very important tool, in supply chain, so many company, I would say most supply chain companies rely on this tool. The technique that proposed in this paper can also be applied to enhance the quality of decisions in the MRP and DRP setting. All right. So just to give you a very brief, short perspective about MRP and DRP. So essentially, um, in this illustration, right? So let's say you want to produce some product. You have the list of components, which we call the bill of materials. So in the bill of material, it gives you, the list of components that need to be assembled together, and then the sequence of the production you need to follow, right? Based on that, you can basically build a table to calculate how much you need to produce for each subcomponent, how much you need to assemble until from the very raw material until the finished product. So it covers from the procurement, production planning, until the delivery, until the end customers. I'm going to have simple illustration to show how these material requirement planning or distribution resource planning are actually used in order to calculate the planning of your supply chain process. So the production components, at the top level, this is also the rough cut inventory, rough cut production planning that also consider different type of constraints. When you figure out this type of, production planning and so on, and then you launch your production, definitely you need to ship the product, right? And then you connect basically you are a manufacturer, now you have finished products, and then you need to basically distribute it through your distribution network. So that in that sense, you start distributing the product, you have this network of the distribution from, regional distribution center, distribute to the local distribution center, and could actually go to the retail. So this process cover from, almost end to end of your company in terms of supply chain in order to manage the entire supply chain in terms of decision of the production and also the fulfillment, right? So as you can see, the material flow would flow from the right to the left. So basically, the calculation of the quantities you need at different time period would go. Sorry, the production and also distribution of material would go from the right to the left. On the other hand, you receive information, meaning the demand estimation that you would estimate at the point of consumption. So if you basically have your own retail stores, basically you calculate or you forecast the demand at your point of consumption, and then you propagate that information in order to calculate the requirement of the quantity of product at different time in your calendar. So let me give you an example. Let's say I take the retail, one of the retail right here, right? You would need to put the forecast, right? And these calculation of material requirement planning or distribution resource planning rely mainly on, I would say like a few magic parameters. So in this case, we need to respect the lot size. So every time, you need to make an order, it need to be 25 units. And you use inventory optimization techniques to determine the level of safety stock. It becomes 5 units. So in the MRP and DRP, the rule of the execution or decision making is very simple. You calculate inventory projection, and one inventory projection would be lower than the level of safety stock, which is considered critical level. You plan to bring that supply or that quantity of product in order to replenish the inventory before it hit the critical level, which is the level of safety stock. So as you can see from this graph, your projected inventory would basically hit the safety stock level around period number 3, right? Around period number 3. So basically, we need to bring additional unit in order to bring inventory up. And because our lot size 75 unit, so I'm going to need to bring 25 unit in period 3. But because it's going to take 2 period in order to bring that 25 unit, the order need to be placed to the upper stage in the supply chain equal to 25 units 2 period before, right? I need to place that. I need to pull that quantity in period number 1. It takes 2 weeks and it will arrive in this location in week number 3. And by that time, you would actually bring up the inventory so that it would not be lower than the safety stock level. So this process is repeated and create this plan order release. And this plan order release is basically combined with other retailer to become the demand of the upper stage in your supply chain. In this case, is a regional distribution center, right? And that process continue at the regional distribution center. You have lot size, you have safety stock, you have like projection. You try to bring inventory up before the inventory become negative. All right. So you can see that this is multi-level planning, and also it has some kind of dependent demand, meaning that the demand of the regional distribution center depends essentially on the subsequent stages in your supply chain. So this calculation starts from the point of consumption. You propagate that information, the calculation to the upstream of the supply chain. And definitely this planning process is basically repeated, for also other products that you have in your supply chain. So essentially, you could also have joint inventory target. You may have substitution effect. In one of the paper, we also consider the substitution, component substitution in the planning process and demonstrate the value of using stochastic optimization, right? So what happened in many cases in supply chain planning is that these two, magic numbers that we use in order to um, um, derive the decisions that you need to make, which is when you need to bring the product um, and also the level of critical stock, which is the safety stock level, come from the techniques that are developed based on different assumptions. So most of the time, the lot sizing problem, right, come from the techniques that develop based on assumption that demand is deterministic. Even though we know in reality it's not deterministic, but we kind of assume that we have pretty good estimation of the demand, right? So if the demand is deterministic static, meaning that the demand, doesn't change so much over time, we have this textbook calculation, economic order quantity. You can use that to set up the lot size. You can also set different lot sizing rule, right? You kind of ignore the uncertainty when you do these type of steps. This is also the optimization model. For example, in SAP, there is as the APO module, or in some other ERP tools, is a module to calculate the dynamic lot size. Meaning, if you can change the lot size over time in order to capture the demand that you anticipate, then you can vary the lot size. And then you can basically model as an optimization model. This also, there are a lot of lot sizing, models that you can use in order to calculate the order quantities or the production quantities based on different constraints. So most of the time, we would bring this type of decision from the literature that assume, or a technique that assume deterministic demand, either static or dynamic, right? But when you face with uncertainty, now we're going to add safety stock, and safety stock come from the assumption that uncertainty is static, stochastic, and then it determine in some many cases using this kind of magic formula. So for example, this safety stock formula, in the textbook is also used, in many calculation of safety stock. So we set some kind of the service level, right? And then that service level is multiplied to standard deviation of the demand. So if we use forecast, it becomes standard deviation of the forecast, which is essentially the root mean square area of the forecast, and then multiply to, I forgot the square root right here. So square root of the lead time, right? The square root of lead time. There are many other formulas, right? That you can use, but basically it comes from, the techniques that develop based on different assumptions. So now you kind of pull together two different type of, the decision that come from different set of assumptions, and then you use that in the decision making process. So our perspective right here is basically, um, if we actually look into this problem into a single problem, right? We try to model uncertainty explicitly. We try to solve this large scale model over the entire network of the supply chain. Is there a value, cost savings, or improve level of service that we can gain by doing such a complex optimization? So we look into different setting in terms of how adaptability of the decision can be, right? So if you assume everything is deterministic, right? You assume that the demand is perfect, right? You have plan receipt, you have plan order release, you make your decision, and then you keep your decision like that. So it become, everything became the here and now decision making process, meaning that you make a decision, you stay with your decision, you don't change your decisions over time. So in that case, it corresponds to everything being the static, meaning the setup or the ordering decisions and the quantity of production and fulfillment are fixed. And then inventory is a result of the uncertainty. So basically, if you have high demand, inventory is lower. You have low demand, your inventory is going to be higher. But you don't change your decisions that you already made. If we allow adaptabilities at different level. For example, you can also make production or fulfillment quantity being adaptive, meaning that you're gonna figure out, the production and fulfillment quantity, maybe only for a next few weeks, and then the actual production and fulfillment quantity that come after can be made in the future after you actually realize more information about the demand from now until that point, right? So in that case, your decision become multi-stages because you need to anticipate different level of demand, and then conditional on what's going to happen in the future, you're going to make different decisions. It could also be the full multi-stage in the sense that you can have the system that is fully dynamic, or the setup, production quantities, and inventory gonna be fully adaptive, meaning that you're gonna change your ordering and setup decision over time based on how much demand you're gonna observe. All right. So I will not go into very detail here, but in the sense of multi-stage stochastic programming, especially in the paper that published in Informed Journal on computing, we actually leverage the technique that is quite efficient in multi-stage stochastic programming, which is the stochastic dual dynamic programming approach. So the basic idea of this type of techniques is basically you can write this multi-stage decision-making process as a nested optimization model, meaning that you're going to make some decision in the current stage, which is period 0, and then based on the decision you're going to make, then you assume some scenarios or realizations that going to happen between now and period number 1. Then you have another optimization decision optimization model or the decision to make, and then you make subsequent decisions. So it become nested decision making process in the sense that you're going to make decision in multi stages. Um, so in that case, we can actually look into this through the lens of the formulation that, similar to in the sense of dynamic programming, or even approximate dynamic programming, in the sense that you can frame it that you want to make some decision right now, and then based on the decision that you're going to make, it's going to impact the feasibility or the decision you can make in the future, and then that component going to be approximated through different techniques. So in the stochastic dual dynamic programming approach, we kind of use the technique through the Bender decomposition in order to transform the nested, the subsequent decisions, and then add that information through the form of cut. So we basically solve those problems and chain it into, using dual information, create Bender's cut, and use that Bender cut to add it to the previous stages in the decision problem. And then you backpropagate that cut generation until the first period. So the process work in 2 phases. In forward pass, you try to figure out the decision you want to make now, 1 period from now, 2 period from now, 3 period from now, and so on until the end. And then you backpropagate the cut in order to capture the quality or the bound of that decisions back to the period number 1. The paper we have actually covered the whole, presentation of the reformulation to make it, applicable to the stochastic dual dynamic programming approach. And, I would encourage you to look into the paper if you are interested in that reformulation. So this also, the relationship between, I would not call it relationship, but this also the comparison between multi-stage stochastic program and also Markov decision process, right? But at high level, conceptually, you can still model multi-stage stochastic program as a Markov decision process. However, that implies that, the state that you're going to observe depend essentially on the previous decision and the previous uncertainty. And the action space you can do is actually subject to the previous action you make. So it make the action dependent on the previous state and previous action. So in that case, you need to augment the MDP, and it may not be the most efficient way to solve this problem by modeling as an MDP, just because the action become, the state dependent, and then you need to augment it. And also the state space would actually depend also on the previous action. So those are the things that we don't actually deal with so much when we model Markov decision process. But if you, want to model its Markov decision process, it's also possible. Now let's come back to the main question and the main application we have. What is the value of doing this stochastic optimization, right? So we compare that with different techniques that can be deployed in such a situation. So the first one is also the average. Deterministic model without safety stock, and as you know from the flow of averages illustration I showed in the beginning, may not be the best idea, right? But we also simulate the case that most companies and most decision makers use in practice, we're gonna determine safety stock, using some magic formula, and then we're gonna also make decision based on optimal deterministic model using, multi-echelon, multi-item lot sizing model, assuming that you have perfect information of demand. But then we're gonna add the safety stock on top of that. So what it means is that you want to plan for the order decisions, and then you want to make sure that the projected inventory will not go below the safety stock level. So that is the version of SS. Um, One complexity when we calculate safety stock is basically when you have supply chain network and dependent demand, right? So this is another layer of questions of where you want to place safety stock. You can place safety stock, at the end of the supply chain, right, at the retail stores, and that also make a lot of sense. Um, so in that case, and in the center production, you can also place safety stock at the finished goods level, or you can place at other level in supply chain. But now it's come a questions of where and how you want to allocate safety stock. So at the basic level, in terms of the production planning, we can place safety stock at the finished goods level. But we also look into a better technique that is, very interesting technique on the safety stock placement, which is the paper published by Grave and Willems since 2008, and there were some, additional paper after that. They focus on, the base stock policy, which is, specific form of the policies. And then they basically come up with the model to actually allocate how much safety stock, essentially how much lead time you want to allocate in terms of the safety stock to different location in supply chain. So we also use that calculations. But again, since that paper focused mainly on the base stock policy, it's basically, consider specific case of the production planning. But we use that technique as a, better technique in terms of safety stock determination. So those are highlighted in red. Those are the techniques that combine deterministic planning, with two version of safety stock calculations. And if we compare that with the stochastic optimization, using the static decision framework, meaning that we're gonna fix, the ordering or production decisions, including the quantities, and then we compare with the techniques based on this deterministic model with safety stock. So the red one is basically the one based on traditional approaches. The blue one are the one based on, different approaches that we propose to deal with the stochastic optimization context. And you can basically see that there's a potential of creating, significant savings and cost savings by looking into this joint problem in a single framework, right? You can basically reduce substantially the operating costs, the expected costs that come from different cost component depending on the cost parameters. Some cases you save from the production setup, some cases you save in terms of inventory. You can also essentially save from the backlog and lot sale, essentially based on the cost parameter that you have in the production process, right? So as you can see, the gap right here is the gap against the case when you know the perfect information. So we basically we don't know for sure that the perfect value of the demand, but we simulate as if we know the perfect value of the demand, and then the gap that you see right here is a gap against that optimization based on perfect information. So you can see that the gaps from traditional approach around, for the static, it could be around 10%. For, in this case, for multi-stage decision making process, it could be around 20%, could reduce to maybe 5% or even lower by, explicitly considering the uncertainty in the decision making process in this context. So in the second paper that I mentioned earlier, we also look into the case when we saw complex multi-stage stochastic programming. The question of that case is basically the scalability, how much we can go. So if we model as a big mixed integer linear program, we are not going to solve, very large scale problem, right? So we basically adopt the SDDP, the stochastic dual dynamic programming. And in the paper, we also show that, it could actually tackle the problem even with 100 scenario per period over 10 periods. So 100 with the, power of 10, which is very large. So if you compare that, we don't show the 100 with the 10 period right here because it's based on our calculation, and the return you get is not so much compared to 10 scenario per period for a 10 period. So basically this one we compare the HTTP with the big mixed integer programming, and you can see that we cannot even fit, in some cases, a mixed integer programming in the memory because the model is just too large. You can see, in some cases, the number of variable could be 10 with the power of 10, and the constraint could be even 10 with the power of 11. On the other hand, by doing this decomposition through HTTP, you can basically tackle this problem and robustify or improve quality of your decisions in the MRP and DRP in multi-stage settings. So this is also the tool that I'm quite interested in further developing and applying into other applications. So I'm moving on to the second component, which is on the transportation. This is a paper on the robust drone delivery with weather information. This paper is also already published with the co-author Shun Cheng and also Lumatang Rousseau. And also we also want to acknowledge the huge guidance from Melvin Sim, who actually give a lot of suggestions and also the guidance towards this paper. So in this case, the problem setting is very, very simple. So we look into the drone delivery problem, right? So as you know, there's starting to be like more and more drone operations due to the traffic, due to various reasons. People start, many companies start exploring the possibility of using the drone for the delivery. It could be due to geographical constraint of the destination. It could also be due to the traffic in the urban environment in the city. So Walmart already started drone delivery in some regions, and Amazon is also very active in this area. Drone is also being used for drug medical deliveries, in order to serve the people who require this type of supplies on a regular basis, right? So what happened with the drone delivery is that, as you know, the drone would need to carry a lot of payload, right? And basically, it has a battery. It needs to carry the product, and the drone itself encounter the factor that is quite important, which is the wind speed and the wind direction. So the wind speed and direction can basically alter the flight time of the drone, and that would have significant impact on the delivery operation and time that the drone gonna make in order to serve the customers, right? So that become the important factor that would impact the quality of the services and also the time you need to spend for the services. So this is an illustration. So the flight time, right, can actually be calculated by taking into account the wind speed and also the strength of the wind. So assuming that if you have the speed and angle of the wind, and you have the customer locations, you can basically calculate the forward flight time, the flight time from the depot that you need to use in order to reach the customers, and the backward flight time based on this wind speed, and then returning to the depot. Right. So we look into this problem because the aspect of dealing with this type of uncertainty and the information about the wind speed, historical wind speed, can also be leveraged. On the other hand, as you can see, the problem setting is actually on the scheduling for the delivery to the customer. So basically, it can also be adapted to other type of uncertainties. If you can basically write the travel time that you need to actually use based on this uncertainty as a function, and then you basically can write that as the uncertainty set or ambiguity set that you can use in the model. So this is actually what quantify the uncertainty that we have right here based on the wind vector, based on customer location, based on the launch speed. Then you can actually calculate a forward flight time and backward flight time. But on the other hand, if the wind vector is uncertain, meaning the speed and angle is actually uncertain, the flight time become uncertain as well. So we need to basically consider that uncertainty in the decision-making model, right? So what we assume here is basically we can, get historical wind observations, right? And then we can use that to characterize the flight time uncertainty based on different techniques, machine learning model, clustering techniques. There are many techniques that you can use in order to calculate the flight time and then derive some uncertainty set in order to be used in the model. So our idea right here is basically to leverage, a different form of uncertainty representation. Instead of looking into scenario set, now we look into ambiguity set and robust stochastic optimization framework. So what we consider here is that how about you can observe, historical flight, historical wind speed and wind direction, and use that in order to estimate the uncertainty around the flight time, the forward and backward, and then use ambiguity set to describe that. To reduce conservativeness, we look into what we call a cluster-wise ambiguity set. So in the sense that if you have this type of data, you can cluster the data, right? And based on each cluster of the data, you can actually calculate statistic associated with that cluster. So for example, if I plot, this is a simplified version because let's assume we have only 2 dimensions. This type of data, if I run clustering algorithm, I say that I want 3 clusters. I can cluster the data into 3 partitions. For each partition, I can summarize important statistic and write the ambiguity set based on that statistic. So this is the form of uncertainty set we assume. You can actually look onto the right-hand side in terms of the meaning or the definition of this component in the ambiguity set. If you have one cluster, you can actually calculate the means of forward and backward flight times, like based on the wind speed. Based on this data, you can derive the mean of the flight time as a result of this function, right? And then that becomes the first piece of statistic. You can also use average deviation, the absolute deviation, sorry, of the forward and backward flight time, and you can calculate this parameter, right? So uncertainty set now, for each cluster, we're gonna describe by using the mean and also the average deviation. You can also consider some other form of uncertainty as well, but in this paper, we consider using statistic around the mean and also absolute deviation. Again, this is for each cluster of the data, And we assume that in each cluster of data, the forward and backward flight time is actually bounded. So it's a minimum and the maximum. And based on number of data points that belong to each cluster, you can also calculate the probability that would be associated with each specific cluster, right? So let's say data points are equally divided, you have 33.33%, and the probability become 33.33%, right, for each cluster. So you can see, instead of having 3 clusters, you have 1 cluster. It become the simple box uncertainty set. On the other hand, if you consider every single data point and you don't have any deviation, now it become like discrete scenarios, or you can also use different form, which could also be the empirical distribution to describe this uncertainty. And this is also the model that we use as the benchmark approach, as opposed to doing this cluster-based ambiguity set. So what we want to also explore is if we allow adaptability, meaning that in the drone deliveries, let's say we assume that there are 2 periods, morning and afternoon. So you plan for the morning, you figure out the sequence of customer each drone gonna serve. Let's say this drone serve 3 customers. You start observing the wind speed. Based on historical data, you see, good correlation between what you're gonna observe in the midday and the wind speed and direction you're gonna observe in the afternoon, right? So what it means is that based on what's going to happen, at the midday before the second phases of delivery, you can adapt your sequence based on what you are going to observe. But right now, because I'm in period 0, which is beginning of the day, I don't know what's going to happen yet, so I need to anticipate. So that anticipation is basically the ambiguity set in period number 1. And based on what's going to happen at the end of period number 1, which is a midday, then I'm going to adapt my decision in period number 2, which is in the afternoon, right? So in that case, you can actually further characterize the subsequent stages of decision conditional on the observation you're going to observe at the end of the period number 1. All right. So essentially, we expand the ambiguity set we had in the in the previous slide. Now it covered 2 periods. So you can see that we have mean and absolute deviation for period number one, right? We also have mean and absolute deviation in the period number two. But period number two is also conditional on the scenario of the observation you're going to observe midday, right? That scenario can actually be the cluster in the period number one. So scenario and cluster in period number one become the same, or scenario can also be, different representation of the observation you can get at the midday. It doesn't need to be the same, or it could also be the same. Um, and then you have the same thing, the bound for the period number one, and the bound for the wind forward and backward pass in the period number two. And you also have the probability associated with the entire sequence or the event, meaning that you're going to observe the data belong to cluster K. You're going to observe midday scenario is the wind speed and direction at the midday going to be, this direction with this type of speed. And then the actual observation you're going to get in period number two will belong to cluster G, which is part of the period number two. So the last part is basically the joint probabilities that, the data point will belong to cluster K in period number one, scenario that occur midday going to be S, and data point will belong to cluster G in period number two, right? So I will not go into very detail here for the sake of time, but there are many papers that already propose, some paper consider the drone delivery problems, but there are some paper that consider deterministic approach, some paper consider stochastic approach, but they also consider location routing or drone facility location. This is also a paper that consider robust optimization, but it's in a static sense, no adaptability, and also with the type of uncertainties that are more simplified. This also the very interesting area of research around the data-driven robust optimization. For example, the use of statistics. For example, if you consider single cluster and you have, you consider the moment information in the ambiguity set. This also already, some technique that proposed for that type of ambiguity set. The event-wise ambiguity set or the cluster-wise ambiguity set that we present earlier has actually been proposed by Shen et al. 2020, and it has also been applied to vehicle assignment or the pricing and production decision in these two papers. This is also a very interesting tool called ASOME, RSOME, that is developed as a result of this type of ambiguity set and robust stochastic framework. So if you're interested, I would encourage you to look into those two and those papers. On the other hand, in order to minimize the risk or associated with the delivery, instead of looking into something like just the time or the cost, we look into the risk index. So that is called essential riskiness index. This risk index is proposed in these two papers, Sang and Sang et al., but they consider the VRP and TSP, but under static deviation model. So there's no deviation adaptability. So in our case, we consider the adaptive decisions, right, and the robust stochastic optimization framework, and we want to demonstrate the value of consider that adaptabilities and also the less conservative robust ambiguity set in order to see the quality of the decisions. All right. So maybe I can skip a little bit here. So this is a riskiness index. So this riskiness index, it looks complicated at first, but this is the risk index that would actually minimize, the probability of being late and also the scale of being late. I will not have time to go into the very detail, but the objective function right here is to minimize the sum of the maximum lateness of each drone at the end of period number one and at the end of period number two. We also have many variables that would describe the schedules of the drone, meaning the sequence of the customer that need to be served using specific drone, and also the last customer, because the last customer is the one that would also define, how much lateness you're gonna encounter based on the schedule that you're gonna have. All right. So this is how the robust model look like, and all the scheduling decision belong to this set. So if you're interested, you can look into the paper. This scheduling decision is basically the assignment of customer to the drone, and also the variable Y that keep track of the last customer in period one, last customer in period two, and also first customer in period number two. These two constraints capture the lateness index. So the lateness index is basically the gamma right here, and gamma is calculated based on this function. So as you can see, there's a supremum right here, there's a max right here, so we cannot solve problem, in this form directly. You can actually put this problem into RSUM, the one that proposed by Chen et al. 2020. And then it will do the full reformulation for you and then figure out, the reformation steps, which is quite sophisticated, and then basically solve the model for you. So ASAM is actually also available in Python, so you can look into documentation for that. But what we did in this paper, instead of using ASAM, we want to be able to solve it by using different techniques. So we come up with the reformulations. So basically we transform this constraint into this form by doing reformulation and duality, and then you transform it by changing this form, the supremum and max, into this type of constraints. So as you can see, the number of constraints now increase significantly. And then instead of solving it by using large, very large model, which may not be scalable, we basically solve it using Brand cut process. So we basically solve the problem without these two constraints. We detect the violation, and then we add the cut in order to improve the solution and calculate the objective function based on the actual latest that um, um, happen based on the scheduling decision you make. And then we continue the brand and bound process, and then evaluate the quality of decision and add the cut in order to correct the value of the riskiness index based on the cut that we generate. So by doing this brand and cut, we can save the solution time in most group of instances, and we can also improve the scalabilities. So let me show you quickly.
Dr. Yossiri, we
Yes,
have 5 minutes maximum. So if you
yeah, I'm
get
gonna
on,
wrap up in maybe
thank you.
about 1 minute. So we actually demonstrate the value of incorporating the uncertainty and also adaptabilities in the experiment in that paper. So the first thing we did is basically based on different benchmark approaches, which one is the best, and then we're gonna take the best benchmark approach and then demonstrate the value of our solution approach against that benchmark approach. So in the benchmark approaches, we actually tested deterministic model, stochastic model that maximize the on-time probability, assuming that we have the full information, we have the data, we have empirical distributions. And we also write a model that based on minimizing the risk index using empirical distribution, and also minimizing the worst case of the risk index. So what it turned out is that the version based on the maximizing ERI using empirical distribution yields the best results. So if you look into maximum probability of laser across all the drones, then it reduced quite significantly from 18% to about 3.4%. The sum prop that probably the closest to the objective we have, it's also reduced quite significantly. So across all the matrices, ERIE is actually the best version. So if we compare that with the cluster-wise ambiguity set, we actually see a lot of improvement in terms of the metrics that we have based on the optimal number of clusters. And then the last one, do we have the value of doing adaptive DRO? And the answer is yes. When you allow adaptive decision, you can improve all the metrics, across, different matrices that we consider here. And adaptive decision allow you to make better quality decision in such a context. All right. So that is what I have in my talk. So I like to end the talk usually with this quote. Uncertainty is an uncomfortable position, but certainty is an absurd one. So even we have uncertainty, there's a systematic way to deal with that, and you cannot avoid uncertainty. So this is a reference of the paper, and there are also papers that on other areas. So if you're interested, they are also available on my website. Thank you very much.
Okay, thank you very much, Dr. Yossiri. What a nice talk, and indeed very nice slides, so clean and crisp. So we have time for one question for the speaker. Does the audience have any question for the speaker? If not, then I will ask one question and then pass it on to the next speaker. So Dr. Yossiri, you talked in your work a lot about uncertainty, and I will just take an example from our everyday life, and we are, let's say, for the transportation problem, often we encounter the situation of congestion. So, could you, highlight some advice on how to model congestion and how uncertainty can be addressed in, let's say, timely arrival to the destination?
Yeah, that's a great question. And as you can see, there's still, many papers that consider those type of uncertainties. And in the context of, operation research and also, transportation optimization communities in terms of, supply chain decisions, we consider this type of uncertainty a lot in vehicle routing problems, right? Assuming that you need to do delivery and then the uncertainty around the route. And mostly we kind of consider that uncertainty as uncertainty in travel time that you're gonna encounter in your deliveries. And the question is that how can you adapt the route, or how can you plan the route for the delivery in such a way that it could be robust, meaning that you have good probability that you're going to be able to serve the customer on time, or it could basically serve in order to minimize the total cost that you can potentially encounter based on the time that driver needs to spend on the road. The complexity of that could also be if you can adapt decision on the fly, that become like online and also multi-stage optimization in a sense. And then, the traditional approach that you can plan everything up front may not be applicable. So in that case, it could also be quite challenging. And there are, techniques that people start to develop to consider that, but that is definitely one of the cases that could be difficult. The other one is also the uncertainty that is dynamic over time, right? Morning, afternoon, noon, there are different level of uncertainty. How can you basically represent that? What is the form of uncertainty that would make sense in order for you to plan the route correctly? So I think that's also an active area of research. I think there's also vast, literature that consider based on different assumptions, and that's also, very practical problem that has a very important application in practice.
Thank you. Yeah, very good. And you also talked about your work on drone delivery and under uncertainty. So you mentioned very important point about battery charging. So what if, let's say, a drone runs out of energy during delivery? Are you looking at, let's say, a replacement drone, or how to handle, let's say, immediate demands in your problem? Are there any advice on that?
Yeah, that's a great point. We have another work that consider explicitly the energy consumption based on the payload. In this one, we assume that first of all, the distance or delivery is short enough, and then when the drone come back, then you can swap the battery. So basically we kind of pre-process the risky route or the delivery so that you can have confidence that the drone can come back. But definitely you can also write a constraint saying that the maximum delivery flight time cannot exceed this, and based on that you can also add additional constraint to ensure that the drone will not deliver to the location that is too risky in terms of the battery consumption. But definitely, yes, that's another very important features. Also the same thing for electric vehicles. The energy level that you need to consider in the delivery. Those are also, the features that people consider in vehicle routing problem and also delivery problem in the context of drone. That is also, interesting and challenging. But yeah, there are good progress in that direction.
Okay. Thank you very much, Dr. Yossiri, for making yourself available. It was great listening to you. Thank you once
Thank you.
again. Okay, now I will pass on to the second speaker of today, and who is with us. I will just give him access to so that he can share the slides. So our second speaker is Dr. Yvonne Taylor, and we are so happy to have him with us today. His talk is entitled System Dynamics Modeling Archetypes and Security. Dr. Yvonne Taylor is the senior researcher in system dynamics at Policy Dynamics Inc. in Ontario, Canada. He has a PhD in public policy and MSc in information and systems science and a BSc in mathematics. He spent over 33 years in the Center for Operational Research and Analysis in Defense Research and Development, Canada. He has been a Canadian Operational Research Society member since 1979 and was president of the Ottawa chapter in the mid 1980s. He has been a member of the System Dynamics Society since 1997 and is currently a mentor in the one-on-one mentoring program of the SDS, working with young people worldwide. Uh, it is our great pleasure to have Dr. Ivan Taylor with us today, and I pass it on to him for his talk. Thank you very much.
Thank you, Anjali. Can everyone hear me?
Yes, we can hear you.
Good, good. Yeah, thank you, Yossiri, for that presentation. I really enjoyed it. I liked Anjali's question as well. It was very close to my heart because when I did my master's degree, I looked at pretty much the same problem, but using queuing networks instead of optimization the way you did. But I was using a simulation of queuing networks because I was looking at congestion in a network of queues. Anyways, but yeah, I thought that was a really cool presentation you did.
Thank you very much.
Yeah, you're welcome. Yeah. Okay, I'm going to share my screen now. Okay, can everyone see my screen?
Yes, we can see your slides.
Yeah, there's an interesting bit of a backstory for this presentation that I'd like to start with. Anjali and Anjali asked me to write a book chapter for her book on advances in simulation and modeling. And I wrote a book chapter on system dynamics, and I guess she liked the book chapter enough to invite me to come to this presentation to talk about system dynamics to the Canadian Operations Research Society. And I asked her, well, I have many things I could talk about. I wonder what I should talk about. So she looked at my YouTube channel and she picked this subject, which is system dynamics archetypes. And I said to myself when she picked it, I said, gosh, that's a really tough subject to talk to Canadian Operations Research Society about, because it's purely qualitative, and as Yossiri did his very highly quantitative work in the previous presentation, my presentation is going to be very light in terms of no mathematics at all, just qualitative diagrams. So I'm a little bit embarrassed by the fact that Anjali didn't pick out one of my more quantitative modeling exercises where I use system dynamics. I guess another aspect of this is that yes, I was in the operational research organization in national defense for 33 years. And about the last 15 years of my time there, I was trying to get the operational research organization interested in system dynamics. And I pretty much failed miserably. I tried to teach people system dynamics in short courses, and basically I couldn't get any traction at all in getting them to use system dynamics. And when I retired in 2012, I decided to spend my full-time effort in system dynamics, and I'm working in this company Policy Dynamics right now. So anyways, going back to this presentation, as I said, this is on system dynamics archetypes, and it's applied to defensive and offensive security. And so when Anjali asked me to give this presentation, I'm not really an expert in archetypes, and I'm not an expert in security. However, Keith Willett, who is the lead author on this presentation, who's not here, he's in California, and he wrote his PhD dissertation and included archetypes in his PhD dissertation. And together, he and I wrote a book chapter for a book called The Handbook of Security Sciences. And we included the archetypes in that chapter. then we went on to write a paper for the International Council on Systems Engineering International Symposium last year on system dynamics and security, but more of a quantitative model. So anyways, this is primarily Keith Willett's work. So, I may not be able to answer all your questions today, and I may have to direct them to Keith for him to get back to you. However, after Anjali suggested I give this presentation, I contacted Keith and I said, are you interested in helping me on this presentation? And he said, sure. And I said, and then I said, well, why don't we write a paper for the International Council on Systems Engineering International Symposium in Ottawa in July of 2025. And he said, okay, yeah, let's do it. So we wrote a paper for the Systems Engineering International Symposium, and we submitted it. It's under review right now. It hasn't been accepted yet. We're hoping it'll be accepted. And but anyways, if anyone's interested in reading that paper, I can send them to you after this presentation. And just another note is that the background I have today here is Ottawa. You can probably tell it's Ottawa, and that's the Shaw Center, I think it's called, which will be the convention center that will hold the International Council on Systems Engineering International Symposium in July in Ottawa. So we're all very excited. I'm a member. I'm an executive member of the Canadian chapter of the CORS organization, and we're all very excited to have the International Symposium in Ottawa next year. Okay, with all that, I guess I'll move on to my presentation. So the objectives of the presentation today are to introduce system dynamics modeling in security, and in particular to explain archetypes and their relevance to security. And archetypes are a specific type of system dynamics modeling. It's a qualitative type of system dynamics modeling. And then I want to talk about the practical applications of archetypes to defensive and offensive security operations. And finally, I'll end with some limitations of this kind of modeling and some areas of future research. Okay, well, as I said, this is going to be completely qualitative, and so I'm not sure if you're all familiar with something called a causal loop diagram. And a causal loop diagram helps to visualize feedback dynamics. And in system dynamics, we believe that we should take a feedback perspective on all systems. And basically, systems are connected, are things that are all connected together, and because they're connected together, there's things that sort of cycle around, and that leads to feedback. So here's a picture of a causal loop diagram, and let me just explain how you read this. So the first thing you'll notice is that there's these positive and negative signs on the arrows. So the arrows mean that there's a causation relationship between the item at the tail and the item at the head. And a positive sign on the head of the arrow means that these two parameters move in the same direction in a cause and effect relationship. So for example, in this case here, we have a gap between the desired state and the current state. And then we see that when we have a gap, that leads to action, and the action leads to improving the current state, and improving the current state leads to closing the gap. So the negative sign on the current state to closing gap is the idea that it's moving in the opposite direction. So so you can trace around these arrows, and then you can see the relationships between these things in a causal way. So it's one way I often explain this to people who aren't familiar with system dynamics is that positive arrows are very similar in many ways to positive correlation, and negative arrows are very similar to negative correlation. However, in system dynamics, we take a bit of of offense to thinking about it in those terms, because we concentrate on causation, and we don't like to think about things in terms of correlation. However, obviously, you can't have causation without correlation. So a way I can explain it to, say, a statistician is that this is similar to some extent to a correlation matrix. Okay, now the other thing I want to mention is these double bars over here. You can see them between action and unintended consequences, and they represent delays in the impact of the action and the unintended consequence. There's a delay. So delays are very important, because it makes it difficult to interpret how actions are changing the system. So basically you can imagine, say for example, in the movie Titanic, they wanted to change the direction of the ship, so they turned the wheel, but the ship didn't turn right away. There was a large delay before it started to turn, and because it didn't turn right away, they couldn't avoid the iceberg. And so that's a real problem, especially for senior leaders in organizations. They expect to see their actions actually result in results right away. And system dynamics often suggests that, hey, there's going to be delays between the time you implement something and the time it actually takes effect. There's going to be an implementation time. And we have to sometimes try to convince senior leaders to be patient and wait until this action actually can get through the system and take effect. So delays are very difficult things for senior leaders to appreciate, and there's something that system dynamics tries to convince them to consider important in their decision making. And then finally, we have these feedback loops, and there's two types of feedback loops. There's only two types of feedback loops, which is interesting because there's only two types of connections too. There's the same and opposite. And there's two types of loops. There's a reinforcing loop and a balancing loop. And in a reinforcing loop, you have a situation where a change in one of the variables ripples through the system and causes a further, if it's an increase, it causes a further increase in that variable. And if it's a decrease, it causes a further decrease in that variable. So let's trace this. We label reinforcing loops with an R and a circle. And so let's look at this. So we have a gap, and if the gap increases, then we take action, and the action then could lead to improvements in the current state, or with a delay, it could lead to unintended consequences. And then the unintended consequences cause the current state to decrease. And then the current state decreasing causes the gap to increase. So basically you see that if we increase the gap and went through the loop that was reinforcing, we would increase the gap further because it's a reinforcing loop. And then we can look at the balancing loop here, and we can say that here we have, a gap that leads to an action, and the action leads to an improvement in the current state. And the improvement in the current state leads to a reduction in the gap. And that's a balancing loop. Basically, what happens there is if something changes in one direction, say positive, it ripples through the system and comes back with a negative effect on the original variable. And similarly, if it's a decrease in the variable, it ripples through the system and comes back with an increase to the original variable. And that's basically all there is to causal loop diagrams, and it's almost all there is to system dynamics. So archetypes. So archetypes are recurring patterns in systems that highlight common challenges and leverage points. So once you understand archetypes, you'll see them all over the place in all the systems that you're familiar with. So they're very powerful ideas. The other idea is that they're really only just a combination of reinforcing and balancing loops. However, the great thing about archetypes is that they highlight both the intended outcomes and the unintended consequences of actions. So it really addresses this idea that with every action, there's both an intended consequence and an unintended consequence with every action. And so, we may not understand these unintended consequences before they happen. So the idea is maybe archetypes can help us foresee these unintended consequences of our actions, and hopefully, if they're negative unintended consequences, avoid them. Okay, so I'm going to look at 6 archetypes here. I'm going to look at shifting the burden, which is one archetype. These are just different types of archetypes. Tragedy of the commons. Everyone's familiar with the tragedy of the commons archetype. And then fixes that fail is another archetype. Accidental adversaries is another archetype. Drifting goals is another archetype. And that's a very important one that you're probably familiar with. If you've never heard the term, you're familiar with the idea. And the last one is limits to success, which I think is something you can really appreciate from an operational research perspective. Okay, so shifting the burden. So the idea of shifting the burden is that we have an over-reliance on symptomatic fixes that diverts our attention from systemic causes. And here's the archetype in terms of a causal loop diagram, and it involves 2 balancing loops and a reinforcing loop. So in this case, for a security problem, we have a router failure that is the problem symptom. And then we have 2 possible solutions to that router failure. The symptomatic solution is to reboot the router, and then that causes the problem to go away. The more fundamental solution is that after a delay, you could have a router reconfiguration and maybe a replacement and improved quality control of the router, which would also make the problem go away. However, we have this side effect, and the side effect is a reinforcing loop. And the reinforcing loop is the idea that because we had a symptomatic solution, it was an expedient repair, and people might consider that acceptable over a permanent fix. So, for example, people might say, why would you do a root cause analysis? Because it's going to take time and it's going to be expensive. Why bother? We're okay now. We don't need we don't need a fundamental solution here. So, but however, the unintended consequence is that this increases the labor expenses now, because if you're going to reboot the system every time it fails, you're going to need a 24/7 presence in the
Dr.
organization to
Ivan,
reboot the presence.
I have a question. Just for the benefit of the audience, could you also explain what is an archetype, and while modeling a problem through system dynamics angle, should we try to identify these archetypes, or so that many of them who do not know what is system dynamics can relate to these 7 types of archetypes?
Yeah, well, an archetype is, if I go back a little bit, an archetype is it's just a type of system dynamics model. It's a very simple system dynamics model that is basically a causal loop diagram that explains the behavior of a system in a qualitative way. So and what these it's actually archetypes were sort of made famous by a book written in 1990 by Peter Senge called The Fifth Discipline. And he brought out about a dozen archetypes, and he tried to describe, how these archetypes actually demonstrated the loops and the relationships between variables that recurred in many systems. So basically, there were recurring patterns in systems, and like I said, because they happen often, they could be quite useful. Because, like I said, once you understand archetypes, you'll see them everywhere you look. So they're just models. They're a type of a system dynamics model. It's a qualitative model, and it's a type of system dynamics model that can be applied to many, many systems. So instead of building one model for one system, this is actually one model for many systems. So it's a model that recurs in many different systems.
Thank you.
So anyway, and as I said, it's a combination of reinforcing and balancing loops. Again, it's just completely qualitative. Does that help, Angela?
Yes, thank you very much.
Okay, I'm sorry I went over that too quickly, maybe. Okay, so as I said, we have this shifting the burden archetype, and we saw that we had two balancing loops and a reinforcing loop, and so in the defensive example, in security, we might think of quick patches to security problems that ignore core issues. So that's shifting the burden. So instead of looking at the core issue, the problem, we look at just doing a symptomatic solution of a quick patch. In an offensive example, it could be overused tools that trigger stronger defenses. So you have a symptomatic use of a tool that you use it over and over, but it triggers a problem because you have stronger defenses because it's recognized. And so the recommendation here is from the shifting the burden model, it suggests that we should invest in root cause solutions. So instead of looking at symptomatic solutions, we should look at root cause solutions. Okay, the second archetype is called tragedy of the commons, and I think everyone is familiar with this tragedy of the commons archetype from economics, and it involves competing for shared security resources in security example. And here's the archetype. It's a little bit more complicated. It involves two reinforcing loops and two balancing loops. The idea, though, is fairly simple. We have a CPU resource, and it's a limited resource, and we have two competing processes. We have a mission process, which is maybe the function that we want to actually accomplish, and then we have an anti-malware process B that is also using the CPU. And basically, the more successful the mission, the more gain we get. So A's activity leads to A's gain, which leads to more of A's activity, which is a reinforcing loop. And again, the malware process, the more activity of the malware, the more security you get, and the more security, the more activity of the malware possible. So then, now that both of these processes are using the same CPU, and so after a delay, where they're continually growing their usage of the CPU, there could become a delay in the gain for each individual. So that we have a negative sign between total activity and gain per individual. And that leads to a reduction in the gain per individual. That reduction leads to a reduction in A's gain and a reduction in B's gain, which then leads to a reduction in B's activity and a reduction in A's activity. And so that's the challenge, is that we have the more these two organizations use the same resource, the less resource they'll have to use in the future. So the defensive example is uncoordinated resource usage in security teams. And the offensive example is multiple attackers exploiting the same vulnerability. And then the recommendation is to use strategic resource management, and that's a common recommendation for the tragedy of the commons archetype. Okay, fixes that fail are the situation where temporary solutions lead to recurring vulnerabilities. And this is the diagram I showed you before. We have a desired state, which is maybe a configuration compliance standard. And then we have a current state, which is the current state of the configuration compliance. And we see that there's a gap between the current state and the desired state, which leads to action. And the action might be a configuration modification. And then the configuration modification can improve the current state and reduce the gap. However, there is a possible unintended consequence that after a delay, we could go back to the original state, do a reconfiguration reset back to the original state even after the assessment that we should have changed and modified the configuration. So the unintended consequences is that you have this good intention to actually make a change, but after a while, people just go back to doing it the old way. And I think that's a common thing that you've probably seen yourself in many situations. So the defensive example is, for example, IP blocking system mistakenly blocks legitimate users, so the team disables the system. And the offensive example is that ransomware prompts better defenses. And the recommendation is to focus on sustainable solutions. Accidental adversaries. Now, this is very similar to Tragedy of the Commons in many ways, but instead of looking at resources, it's sort of a situation where the processes that people are using are conflicting. So we have conflicting security measures among teams. And the idea here is that we have these many reinforcing and many balancing loops, but it's similar to the limits to the Tragedy of the Commons, except that these are processes that are, so basically this is also another way to look at this is something called the success to the successful archetype. So here we have A's success on the left-hand side, and A's success leads to more activity toward A. And then we have on the right-hand side, we have B's success, and B's activity leads to more success. And so, however, these two people's success will compete to some extent, so that A's success leads to B's problems of not achieving their goals, and similarly, B's success leads to A's problems achieving their goals. So it's the processes that are involved here, not the resources. So it's just slightly different from the Tragedy of the Commons. So the defensive example is that IT versus operations priorities might be different, as we know that operations is interested in getting things done, and IT may be interested in security, and the more security, the more difficult it may be to get things done, and so that could be a conflict. In terms of offensive example, competing attackers inadvertently alerting defenders. So this is basically two different attackers or two different groups of an organization are inadvertently attacking the same system and therefore alerting the defenders. And that's creating a problem with their ability to meet their goal. And the recommendation here is to foster collaboration and communication. Okay, drifting goals. Now, this is one that everyone knows, I think. It's lowering security standards over time. And here's the archetype. It's two balancing loops. And, I think most of you people are probably professors at universities, and you know that drifting goals is very common among students where, they may strive for an A in a course, and then they get a B in the course or a B plus or an A minus or whatever. And then they say, oh, an A minus is good enough. So they let their goals lower because they achieved them rather than keeping them high and striving for the goal. So instead of saying that they didn't achieve their goals, they just lower their goals to be lower than what they originally suggested they were. So anyways, here in this archetype, we have two balancing loops. So again, we have a compliance standard and an option, snapshot of the operations, the current state. So the desired standard is the desired state, is the compliance standard. The current state is something that's not quite up to the standard, so there's a gap. And then again, we have actions to improve the system, which improve the current state and reduce the gap. That's the lower circle. And so that's the gap closure activity. However, we have non-compliance, and because there could be pressure to adjust the goal. So basically, that would be someone saying, "Stop telling us we're wrong. Change what you want, so we'll be right." So you can see that that would reduce the desired state, and by reducing the desired state, it would reduce the gap. So that also closes the gap. If you can close the gap by improving your standards, or you can reduce the gap by reducing your goal. Okay, so the defensive example is reduced compliance thresholds, and the offensive example is settling for less ambitious targets. And the recommendation here is to maintain high standards and strive for improvement. And the last archetype I'm going to talk about today is limits to success. And I think this is something that operational research people will really appreciate. And this is the idea that constraints on growth may be due to limited resources. So this is the classic operations research problem of optimization subject to a constraint. Maximization of growth subject to a resource constraint. So I think that this should be a very understandable to most people in operations research. And here's the archetype. So you see we have on the left-hand side we have a reinforcing loop, and on the right-hand side we have a balancing loop. And in the left-hand side we see that we have a security investment that leads to growing action, and the growing action improves the current state. And then the improvement of the current state could lead to more growing action in a reinforcing format. However, we have a limiting state, which is the budget. And the operations budget is limited, and there's alternative needs for the budget. So the improving the current state could actually lead to changes in the budget that lead to reducing the current state. So basically, once you start reaching the threshold of what you're allowed to spend, you're no longer able to improve your state. And so obviously a defensive example is budget or personnel shortages, and an offensive example is possibly skill gaps in using advanced tools. And the recommendation is to balance investments in tools and skill development. And I love this word balance. And I think as operational researchers, you can appreciate this is basically saying, what are you getting for your money in terms of your budget? And as we know, you want to be on the Pareto frontier. So you want to be in a situation where you're getting the best return for the dollar you're spending. You don't want to be in a situation where you could get more security for the same amount of money, or the same security for less money, which would be when you're below the Pareto frontier. So basically, this is a very simple thing for most operational research people to appreciate. Okay, that's all my archetypes, and I have a few recommendations for security organizations, and that is to adopt systemic thinking and address root causes. And these come directly from the archetypes. And then foster coordination among teams, allocate resources strategically, commit to continuous improvement and training, and evaluate long-term impacts of strategies. And these are sort of motherhood statements, but as I said, I think you can appreciate how these things come into play with these potential avoidance of unintended consequences. Now, limitations of system dynamics modeling, there's a number. The first is that I specialize in quantitative system dynamics modeling, which uses stock and flow diagrams, which are basically deterministic models of fluid flows in a system, and it uses differential equations, first order differential equations, and it solves them using numerical methods. So so you need to have data, you need to have equations, you need to have the system built in a way that you can write the differential equations, and so it's very quantitative. However, when you're looking at causal loop diagrams that are qualitative, converting those qualitative causal loop diagrams to quantitative system dynamics models in stock and flow diagrams is not always obvious. And so that's a limitation with the system dynamics approach. As I said, there's sort of two approaches to system dynamics. There's these causal loop diagrams, qualitative work, and there's the quantitative work of differential equations and simulation and quantitative simulations. And so, like I said, I specialize in the quantitative simulations, and so that may be why I'm not the best person to explain the causal loop diagrams. And then there's obviously the difficulty in modeling unpredictable human behavior and irrational human motivations. So, as this is all about organizations. It's about, say, security operational people in operational organizations. It's about attackers in hacking organizations. And these people may not be predictable, and they may not be rational at all times. So it may be hard to model their behavior, and put it into a simulation. That's the challenge. And then there's also a challenge with trying to develop real-time decision making with system dynamics modeling. Generally, system dynamics modeling is very good at long-term work and projections into the future. In terms of real-time decision making, trying to have a quick reaction, I'm not sure that system dynamics might be the best method for that. And the last one is that system dynamics modeling, as you probably got an appreciation of just today, is what they call a data poor methodology. And so it's been criticized because it generally doesn't try to collect a lot of data. Mostly it'll make assumptions, and it'll base its work on theoretical extrapolations of those assumptions to their logical conclusions. So so it's assumption based, and it's using very limited amounts of data, and that conflicts a lot with decision makers today and leaders today who want evidence-based decision making, and they may not be happy with assumptions that system dynamics people may make. So there's also these data-driven techniques such as data science, data analytics, machine learning, and all these things. And so integrating system dynamics modeling with data-driven techniques is something that's needed in the future, and I'm going to talk about future work in the next slide. So future research is that we need to adapt system dynamics model to real-time data, as I said in the previous limitation. And here's some applications in security-oriented system dynamics modeling that I haven't seen a lot of literature on. One is the Internet of Things. I haven't seen a lot of SDM on that. The other is cryptocurrencies. Maybe I'm just missing the literature on that. And quantum computing. I think quantum computing is going to be a huge problem for security people in the future. And then the last one is the ethics of using system dynamics modeling for offensive security, and that's basically hacking. But one of the things I think might be interesting here is that let's say that there's unintended consequences with an offensive operation. as a defensive person, you might want to try to trigger the unintended consequences of the intended consequences of the hacker. So if you could somehow use your knowledge of archetypes to trigger these negative unintended consequences in the hacking, you might be able to actually do better at your defensive operations. Okay, key takeaways here is maybe there's a value in system dynamics modeling in anticipating long-term security impacts, and how archetypes can be used to anticipate unintended consequences. And like I said, it's so important to recognize that every action you take has both an intended and an unintended consequence. And the need for systemic thinking to enhance security resilience. And here's some references. You probably can't read them, but there's one reference here that I want to just highlight. It's near the bottom. You can see it maybe Keith Willett, Keith E. Willett and Ivan Taylor, System Dynamics Modeling Archetypes and Security in COSI International Symposium 2025, Ottawa, Canada, July 26th to 31st, 2025. And like I said, that's the paper I wrote. It's a short paper. We wrote it based on this presentation for the INCOSI conference. And if you're interested in getting that paper, just feel free to contact me. Thank you for your time and your attention, and I'll open the floor to questions. I think we have lots of time for questions if there are any.
Okay. Thank you very much, Dr. Taylor, for your insights and great presentation. So the floor is now open for questions. Please ask any questions if you have to Dr. Taylor. Okay, so I will maybe just begin. So Dr. Taylor, system dynamics, as we see nowadays, is becoming more popular, and many researchers are using it to solve or to model complex problems. However, in system dynamics, when we are developing causal loop diagrams, the relationship between the variables for new type of problems or problems which are exploratory in nature, what is your advice on the relationship building between the different variables? Often we rely on statistics or other type of data, but there may be instances such as, for example, the drone problem, one of the speakers talked about today. So let's say if we are investigating drone applications in logistics and we want to use system dynamics modeling to investigate its application in the area. So in that case, maybe we are not aware of a relationship between all the variables, system variables. So do you have any advice on new researchers who are trying to build system dynamics models and want to identify the relationship between these variables? Sometimes we use judgment and may use, direct relationship or indirect relationship, but in reality, it may be, I don't know, there may be a nonlinear relationship, or it may be x squared versus x and so on. So how flexible we are there, and what are, the concerns we should be worried about if we do not have exact data to model exact relationship between the variables. So how to proceed in those cases?
Yeah, that's a really important question now, and I have to answer that question all the time in my work. And one of the things I think that I recommend for especially for young people I'm mentoring is when they start to work on a problem, they should immerse themselves in time series data. So they should collect as much time series data on the problem and the variables in the problem as they can find, and really immerse themselves in the data and try to understand what the patterns in that data is. And as you say, these patterns are often nonlinear. So statistics will only get you so far in looking in understanding the patterns. You have to actually look at graphical displays of the time series to actually appreciate some of the nonlinearities in the data. And so first of all, like I said, you collect time series data and you immerse yourself in it. And then what I generally try to do is it's recommended by the people in system dynamics to build a hypothesis. And the hypothesis is basically a causal loop diagram, and build a hypothesis that it's called a dynamic hypothesis, but build a causal loop diagram that actually could explain the patterns in the data. So what in system dynamics we call the data, we call it reference modes. So we have these reference modes that are historical patterns in the data, and then we have to try to develop a hypothesis in terms of a causal loop diagram as to why these patterns happened, and how did these patterns happen in the data based on some kind of causal relationships. And then once you have that, you can start thinking about developing equations, and then you can build your equations and run your model as a system of differential equations, and then you can go back and like, for example, the thing about system dynamics is we're interested in the future. We want to know what's going to happen in the future, and so that's that's important. However, if you talk to a decision maker about your model, first thing he'll ask is, how did it do in the past? Did your model actually replicate the past behavior? So you have to what we call calibrate the model. So we calibrate the model to the data to try to show that, yes, this model can actually model things that have happened in the past. And then hopefully that builds confidence that the model is a valid structure for the system. And then we can say, now we have a valid structure for the system, and we can use that structure to project into the future what behavior might happen in the future. So there's definitely a methodology there that is used for building models, and it does, although I said that system dynamics is data poor, I really think that it doesn't have to be. When I collect time series data and calibrate the model to data, then I find that I have collected a lot of data, and so for example, a recent model that I built, I collected 10 years worth of daily stock market data on a company, and I used that data to fit my model to the data, and it got me a nice fit to 10 years worth of daily data. So that's a lot of data. So yeah, so
Sure.
that's the kind of thing that we would do, like I said, to try to generate those relationships, like you said.
Okay, thank you. Brandon has a question. He asked, Brandon, would you like to put your question? He asks, does this framework take any theory or ideas from structural causal models or potential outcomes?
Structural causal models. Yeah, I think it's definitely the same concept. Structural causal models. I don't know exactly what Brandon's referring to, but I will sometimes present my models in matrix format, where I have all the variables on the x-axis and all the variables on the y-axis of a matrix. And then I'll put plus and minus signs in the cells to represent the positive and negative connections between those variables in a causal connection. Now, causality is a very difficult concept, to prove. Like I said, you can say for sure that if you don't have correlation, you don't have causality. But proving causality is a very difficult thing to prove. Maybe there's techniques that I'm not familiar with, and maybe Brandon, some techniques for proving causality. But I don't use them myself.
So
Hope
are
that
there
helps,
any more?
Brandon.
Sure. Are there any more questions for the speaker? If not, then we would like to thank Dr. Yvonne Taylor for according us his important time and presenting to us about the various system archetypes. It was great knowing about your work and to
Yeah.
listen.
Yeah,
to the
another
presentation.
thing is I hope you'll share the video with me.
Yes, indeed. I will after
And
the
I'll
talk.
post it on my YouTube I'll post it on my LinkedIn channel. So
Sure,
if
it
anyone
will
wants
be.
to connect with me on LinkedIn, I'd be happy to connect and you can see
Sure.
all my videos there.
Sure, I think it will be of great value to our audience as well. Thank you very much, Dr. Taylor. It was great having you with us, and I will
Okay.
share the link once it is ready. Have a great day.
Okay, bye-bye.
And thank you to everybody for attending. Have a nice day.